In this section, we're talking about energy and momentum in electromagnetic waves. Now, what we know is that all waves transmit energy, and electromagnetic waves are not any exception. In section 26, we showed that the energy density of an electric field of magnitude E is equal to this amount. In section 9 of chapter 23, we showed that the energy density of a magnetic field of magnitude B is shown by this expression here. Now we can say that the total energy density, that we call it U, of an electromagnetic wave is simply the summation of both these equations. So as we expect both electric field and magnetic field contribute to the total energy carried by a wave. Not only that, but also we can show that the electric and magnetic energy densities in an electromagnetic wave are equal to each other. And this again shows the symmetrical role played by the electric and magnetic fields. So I can write the total energy density of the electromagnetic field in this form. Because E and B, they vary with time, it follows that their average values are zero, just like the current or voltage in an AC circuit. We have studied this before. So to find the average energy density of an electromagnetic wave, we must use the RMS values of E and B. Recall that the RMS value of a sinusoidally varying quantity is related to its maximum by the RMS value equals to max or peak value divided by square root of 2. So I can write the RMS values of electric field and magnetic field in terms of their peak maximum. So if I set the energy density of electric field and magnetic field equal, and then I replaced everything by the RMS values here, then I can just conclude that E equals to this amount times B. Now it's good to know that this amount here is exactly the speed of light in vacuum. So I can write E equals to C times B. We can use this equation to solve tons of problems. As a practice, there is an exercise in your book 25-7 that says at a given instant of time, the electric field in a beam of sunlight has a magnitude of 429 newtons per coulomb. What is the magnitude of magnetic field at this instant? All right, so I know the amount of the amount of electric field, and I'm looking for the magnitude of the magnetic field. So using the previous equation, I can write B equals to E divided by speed of light equals to 429 newtons per coulomb divided by 3 times 10 to the power of 8 meters per second. And if we calculate this, magnetic field will be equal to 1.43 times 10 to the power of negative 6 Tesla. Another quantity that we need to learn is the intensity of an electromagnetic wave, which is the amount of energy a wave delivers to a unit area in a unit time, and we call it intensity. I'm going to jump directly to the equation without deriving it, and the intensity equals to energy density times the speed of light in vacuum. I can write this in terms of the electric and magnetic fields, and because I know that this summation is equal to the total of electric field or the total of magnetic field energy density, I can rearrange this equation and write it in this form. Notice this as before, to calculate an average intensity, we must replace E and B with their RMS value. So always remember that for the average value, we're going to put the RMS values of electric field and magnetic field. Let's solve example 25H together. A garage is illuminated by a single light bulb dangling from a wire. If the bulb radiates light uniformly in all directions and consumes an average electrical power of 50 watts, what are the average intensity of the light and the RMS value of E and B at a distance of 1 meters from the bulb? For solving part A, you need to recall that intensity is power per unit area. Intensity is power per unit area. And this is important to recall here. Okay, in the problem, it says that assume that 5% of the electrical power consumed by the bulb is converted to light. So not all the electrical power is converted to light, but only 5%. All right, and then the distance is given to be 1 meter from the bulb. Okay, so the area, if the distance is R, the area, because it is the light bulb and it is a sphere, the area of the sphere, and this is only the surface area is 4 pi r squared. Okay, now the average power of the light is 5% of 50 watts. So I'm gonna write I average to be 50 watts times 5%, which is 0.05, divided by 4 pi r squared. And this gives me 0.199. Okay, the unit for intensity, as you can see from the equation, it's watts per meter squared. In part B, we are asked to find the RMS values of E and B at a distance of 1 meter from the bulb. All right, so for solving this, we just simply use the equations that we had, and on your book, it's equation 25.10. As I told you, whenever we are looking for the average value, then we use the RMS value for the magnetic field and the electric field. So from here, I can solve ERMS to be square root of I average divided by C epsilon naught. And then from the equation that I had for magnetic field, I average equals to C divided by mu naught times B RMS squared. So B RMS is equal to square root of mu naught I average divided by C. Now it's just a matter of plugging the number in and use your calculator to calculate this. Do not forget that the unit for B magnetic field is Tesla, and then for electric field you have Newton per Coulomb. Okay, in this section we are talking about polarization. Now the simple incident that comes to our mind when we talk about polarization are the sunglasses that are polarized, or as they're advertised, it can block the light. Well, we'll see if this is true or not. Now, imagine that you're looking into the blue sky on a very clear day. Now, you can see the light that is fairly uniform. But for some other animals, for example, the honeybee, the light in the sky is far from being uniform. And the reason is that the honeybee's eyes are sensitive to the polarization of the light because disability helps them in their navigation from hive to flower and back. Now, what is the meaning of polarization exactly? To understand the meaning of polarization, I want you to go ahead and read page 897 on your book together with the pictures and figures that you can see, because if I want to just write it here, it's going to be like a long lecture, and the file will be too big to be uploaded on YouTube. But simply put, polarization defines the direction of the wave, the direction that the wave is oscillating. Now, something can be horizontally polarized or vertically polarized. And then we have unpolarized light. For example, the light that comes from the light bulb or from the sun. They are just like propagating in or oscillating in different directions. They don't have any direction. And then we have stuff that are called polarizers that help us to polarize an unpolarized light. The polarization or the direction of the polarization of an electromagnetic wave is the direction along which its electric field oscillate. So let me write this for you because this is very important. So the polarization of an electromagnetic wave is the direction of electric field oscillation. All right, so if an electromagnetic field is vertically polarized, then the direction of electric field or the direction of oscillation for electric field is perpendicular to the direction of propagation of the wave, as you can see in this picture here. Then if the light is unpolarized, and if this is the direction of propagation, direction of propagation, then this means that electric field does not have a specific oscillation direction. So this means that the polarizations are in all directions. So I can just show it by this. So this is the electric field that is oscillating in every direction. So this is an unpolarized light. But then if you want to show a polarization, you use a double-headed arrow. So this is the direction of the oscillation for the electric field. Now we consider what happens when a beam of light polarized in one direction encounters a polarizer oriented in a different direction. Now you can take a look at figure 25, 24 on your book, and then you can see the light which is vertically polarized and has an intensity I0 passing through a polarizer with its preferred direction that is called its transmission axis at an angle theta to the vertical. All right, so for describing this situation, we use a law that is called Malus' law, or the law of Malus. So this law gives the intensity of the polarized light after passing through a polarizer. According to this law, the intensity of transmitted beam equals to the initial intensity times cosine square of the angle of the polarization, or the difference between the axis of polarization and the vertical axis. Now, what we need to pay attention here is that the intensity is unchanged if theta equals to 0, and the intensity becomes 0 if theta equals to 90 degrees. So if I want to show theta with vectors here, if this is the direction of electric field, this is theta, and this is E cosine theta. Let's see how we apply this Malus law. Now in exercise 2511, it says vertically polarized light with an intensity of 428 watts per meter squared passes through a polarizer oriented at an angle theta to the vertical. Okay, so from here I know that the initial intensity is 428 watts per meter squared, and again pay attention how this is the unit of power and this is the unit of area, so intensity is power divided by area. Now this beam of light passes through a polarizer that is at an angle theta to the vertical, so we are going to find the transmitted intensity for that light for theta equals to 15 degree first of all. Okay, so if theta is 15 degree, according to the Malus's law, then I equals to initial intensity, which is 428 times cosine square of 15 degree. So that will give us the intensity to be 399 watts per meter squared. All right, so for theta equals to 45 degree, then the intensity is going to be 428 times cosine square of 45, and the result is 214 watts per meter squared. And then for theta equals to 90, as we expect, then I is 428 times cosine square of 90 degree, which is 0. Another very important result is the transmitted intensity for an unpolarized beam. So this law, the Malus's law, is only used when the first beam of light is polarized, but then the direction of polarization changes. But if the original beam is unpolarized, so for unpolarized beam that passes through a polarizer, then I equals to half of initial intensity. Just keep this in mind, that instead of using cosine square of theta, you just make the initial intensity half if the initial beam is unpolarized. Let's just solve this quick example 25.13 before we end this chapter. On this example, it says that calculate the transmitted intensity for the following two cases. So let's solve case A. Well, part A is simply very similar to the exercise 2511. So let's go ahead and do part B. I let you study part A for yourself. So in part B, it says a vertically polarized beam of intensity I naught passes through two polarizers. The first with its transmission axis at 30 degree to the vertical. So the first one, theta is 30 degree. And the second with its transmission axis rotated an additional 30 degree to the vertical. All right, so the final beam is polarized at 60 degree to the vertical. So it goes through 230 degrees, which is 60 degree. So we want to find the transmitted intensity. So what I need to do here is that I need to apply this equation twice. So what happens here And let me for now get rid of the second case. It passes through a polarizer that has the transmission axis of 30 degrees. So just write that the transmitted beam, the transmitted intensity of the beam after passing through the first polarizer is going to be I naught cosine square of 30 degrees, because this is what the problem says. So it's going to be I naught, then cosine of 30 is square root of 3 divided by 2 squared. So it gives me 3/4 of the initial intensity. So this was the first polarizer. Okay, then this beam will pass through the second polarizer. So the beam that has the intensity of 3/4 of I initial is now passing through the second polarizer. The second polarizer has again the angle of 30 degrees with vertical. Okay, so I'm gonna do it again. So 3/4 of I naught cosine square of 30 degrees, which is another square root of 3 divided by 2, all to the power of 2. So the final transmitted intensity is going to be 9/16 I naught. So for the polarization, it's important that you do it one by one. For example, if it said that the initial beam was unpolarized and then it passed through a polarizer with theta 30, so what you would do was that the first time it will be half, and then the second time, or the final time, it's gonna be what it was after passing through the first polarizer times cosine square of 30 degrees. Now, so on, if it passes through another polarizer, for example, with transmission angle of 60, then I'm gonna multiply this by cosine square of 60, and so on. All right, so this brings us to the end of this chapter, chapter 25, and this is as much as I want you to understand and learn, nothing more than what we talked about in the videos. Like always, please feel free to email me or inbox me and ask me any questions. Stay safe and stay healthy.